Hello guys. Now we'll look into uh, module 4, that is visible surface detection. So we now will talk about two algorithms mainly. That is backface elimination algorithm. And the next one is Z buffer algorithm or depth buffer algorithm. Now, what is this visible surface detection? I'll make you understand in this way. Given a problem, given a scene where you have a scene like this, there is a cube, 3D cube. What exactly you will see here? For example, if you look at front face, that is at this angle, you will only see three faces, which we apparently saw in uh, lab program number 3, lab program number 4, and okay. So if the viewer looks at this angle, the front view angle, he will only see the front face, top face, and the side face. What about the back face? What about this left face? And what about the below face? We human beings, we understand that those three faces are not visible. But how exactly you make the machine understand about this? That is what you mean by visible surface detection. That is, whichever the surface is visible, you need to first detect it and then show only those faces. Other authors or some authors will also call this topic, this uh, problem as hidden surface removal. So whichever those surfaces which are hidden, to remove it. So either ways, either you can show those faces which are visible, that is visible surface detection, the phrase. The other phrase is hidden surface removal, both the same. There are various algorithms like backface elimination, depth buffer, uh, ray tracing, A-plane method, many things. So here we'll talk about these two. There is backface detection and depth buffer or Z buffer. Z buffer and depth buffer, both are same. All right. First, we will understand why you need to do this hidden surface removal or visible surface detection. Here I gave you one example. One more realistic example. Let us say there are three objects. Each, some portions are getting coincided with some other portions with the other object. So you can see this green ball is coincided, or some portions of green ball touches with this red colored brick, and this yellow colored triangle coincides with some faces of this green ball. So ultimately, you need to remove these portions, or you should not make the user see these portions. Right? So that is the reason you need to either do visible surface, either detect the visible surface or hide the back faces. I mean, hide those surfaces which are not visible. So there are two approaches mainly. That is, I can say the entire range of algorithms, whatever we have, some 8 to 9 range of algorithms, are being basically classified into two types. One is called object space method, one is called image space. Object space method is by far the least uh, efficient method. Here, what we will do is it will compare objects and parts of the the object of the scene to each other. That is, I can say you can see some parts of this green ball will be now compared with the some parts of red color brick to determine which surfaces are visible. This is called object space approach. Next one is called as image space approach, wherein what we will do is visibility will be decided point by point, pixel by pixel on the projection plane. Now, here we discussed that we will discuss two algorithms that is called backface detection and depth buffer method. This backface detection falls into this object space method, and depth buffer or the Z buffer algorithm comes into this image space. Now, image space method is by far the most accurate and commonly used algorithm. That is your depth buffer algorithm. We will see that later. All right. There can be full, the overlapping of the images can be full, can be partial, can be none. For example, let us take this image and one more image, square, so which completely overlaps with my small triangle, something like this. So what you need to do apparently is you need to fully hide the triangle because it is not seen. So hidden surface removal means just hide the entire triangle surface. This is called full occupation. Second one, there is a triangle, and then goes another one which partially covers. So you need to hide the upper portion of this triangle. Third one, there is this triangle, and there is one more square. So no hidden surface. So entire thing is completely visible. Now the point is all these can be easily understood by a human being. How do you make the machine understand? That's the tricky part. All right. Now we'll first apply the object space. There is the backface detection method. Now the simplest thing you can do is just discard whichever pixel is not visible. That is the meaning of backface detection. So in order to remove the unseen faces, first you need to detect it. So how do you detect it? Just project it, and whichever pixel you see, just show it. Whichever pixel you don't see, just don't show it. But the real mathematics comes. How do you exactly know, or how do you determine which pixel is visible to the machine, to the camera, which pixel is not visible to the camera? There is some mathematics. Okay. Before going to that mathematics, let us understand in this way. Now, the user is here, you can say the camera is here. He is seeing this object. Now, which face will be visible? These faces will be. You can see here, this face. Which faces are not visible? The remaining faces. These faces are not visible. Repeat. The polygon is here, and the face that I can see from this angle. Visible surface detection. I am only detecting these faces. The other faces are not visible. Now, what are we doing? We are actually doing back face detection. What is this? This is the first algorithm that we need to do. Back face detection. That comes in object space classification. Now, how exactly you can do it? How exactly you can make the machine understand that these two faces are visible, these four faces are not visible? Now, the mathematics says you view, and whatever you view, that is called as V, vector V. Now, draw a normal to the plane and multiply these two vectors, something like this. You view, this is your view, this is the projection plane, and this is the normal, the perpendicular line. Now, if the normal line into the view, if you multiply it, and if that becomes, if the answer is more than 0, that means that particular face is backwards. For example, you are viewing an object which is here. This red color line is the projection plane. This dotted view, this line is the view. V, this red is a projection plane. You draw a normal. Now this V into N, if that is greater than 0, that means this face is back face. So this is how I make my machine understand that this face is back face. On the other hand, on the contrary, let us say there is an image here. You are viewing, this dotted line is your view line, that is V. Now this yellow line is the projection plane, and you draw a normal 90 degree. Now this V into the normal N, if you multiply it and if that is less than 0, that becomes your, that means this object is front face. Simple. In OpenGL, we say as cull face. Cull means eliminate. Here, we are eliminating the back face. Now, in OpenGL, you can just specify GL cull face. Now, which face you don't want to see? GL back means the back face will be eliminated. But how exactly GL cull face works is this normal into view. Remember, we had discussed GL you look at. So wherein the camera looks at, really look at as 9 parameters. So we can show which face is visible, which face is not visible. In the teapot program, we discussed that. How exactly cull face works is this way. Now, to understand these mathematics, what is N, what is V, we can simply look at this. So where is vertices, and N is your normalized normal, calculating the normal. You can calculate the normal with the cross product. That means to say how exactly you can do this in the end dot. This is how you can. Now these, that means there is a polygon, you draw a normal, these faces are visible. Why? Because n into these faces, you multiply, that becomes less than 0. Less than 0 means it is front face, more than 0 means it is back face. So now those faces are not visible. Now, if you just go back to the third program and the fourth program, I had discussed this. In the cube, there are 6 faces uh, at any given point of time. Normally, 3 faces will be visible. How exactly we made the machine understood those faces? We traversed those vertices counterclockwise, didn't we? So that we made the machine understood that those faces are front faces. When you traverse clockwise, that is called back facing. That is, these back faces are not visible. How did we make the machine understood front face and back face in our lab program, that is third program and fourth program? By traversals. This is also one way. And apparently, if you do this mathematics will indirectly happen. All these are uh, back face detection. Just to summarize, from the Hearn and Baker's textbook way, any plane, you can see these are all planes. All these are planes. Any plane equation, of course, we know the plane equation ax plus by plus cz plus d. This plane equation, if the normal and the view vector is less than 0, what we saw here is less than 0, it is front face. Or other words, if the plane equation is less than 0, it is front face, it is visible. Whereas if this plane equation, that is the n into v, this n into v is greater than 0, means it is backwards. Here. So this is the plane with ABC faces with this equation, and apply the mathematics. If it is less than 0, there is back face, sorry, front face. If it is less than 0, front face. Greater than 0 means back face. So this is what we this I can say this is a summary of your backface detection methods. But as I already told you, backface detection, that is culling, backface culling, falls into the uh, object space category, which is having less accuracy. That is why industry doesn't use this. So industry prefers the depth buffer method, or I can say the Z buffer method, which falls into image space category. Depth buffer algorithm, or I can say Z buffer algorithm, is an efficient algorithm to determine which face is visible, which face is not visible. Or to put it in simple terms, use Z buffer or depth buffer algorithm just to highlight which pixels are visible. That's it. Now we'll look into the algorithm later. That is in another 5 minutes. Let us understand via common sense. Let us understand this algorithm via common sense. Now depth buffer. To understand depth buffer algorithm, you need to have two buffers. One is called color buffer. One is called depth buffer. What is this? I'll tell you. Color buffer means for every pixel in the image, you tell me what is the color. For example, let us take this pixel. Now this pixel's RGB, let us, if we consider this as a red color image, so this will be 1, 0, 0. This is all, I mean the entire, this ground face is 1, 0, 0. If you imagine this as a red color. Now, let us take this wall. This wall is made up of 1,000 pixels. Imagine each pixel RGB values you should store in color buffer. So this is called as color buffer. Each pixels RGB values. If you imagine there are let's say 5,000 pixels in this image, so 5,000 into 3. So those many values. Basically an array. 1 cross 3. Next, what is depth buffer? For every pixel of this scene, you need to consider the depth value of it. What is this depth value? I'll tell you. Now store all these 5,000 pixels depth value. How do you calculate depth value? I'll talk about that in a bit. Please store all these 5,000 pixels depth value in a memory called as depth buffer. Repeat, to understand Z buffer or to understand the depth buffer algorithm, we require two buffers. One is called color buffer, one is called depth buffer. In color buffer, how many ever pixels we have, those pixels RGB values will be stored in the memory. The depth buffer means how many ever pixels we have, every pixel's depth value, that is the Z value, depth value, which I'll talk about that in a bit. Depth value will be stored in this array called depth buffer. That is the storage called depth buffer. Keeping these two, how do we do it? Now, please understand Z buffer, that is, you have calculated somehow. I will let you know that somehow later. You have somehow calculated all the pixels depth and stored in this depth buffer. And you have, and somehow you have calculated the RGB values. But what we will do is we will now understand that all the colors are, let us say, background color. That is, I can say, if the background color, now you can see here this image and this surface. So this image covers this surface. So the background of this image is not visible. So you can consider that background, let us say, as color as 1, 1, 1, no white color or 0, 0, 0 as black color. That means just fill that background color for all the values. To make this simple, to make this to put this in a simpler way, let the Z buffer for all these pixels be infinity, or I can say highest. Screen, you can see everything is empty. Means I can say as a black background. That is, you are not seeing anything. So initially, let us understand in this way. So Z buffer means all the pixels depth is infinity, because let us initialize the algorithm, initialize the buffer, and screen let us initialize to be empty. Okay. Now let us take this as my image. This all these purple dots. The entire thing is my input image. Okay. Now this part is your depth buffer. This part is your screen buffer. In the previous slide, depth buffer is infinity, screen buffer is empty. Okay. Now we have this image. Let us say somehow you have calculated the depth value of all the pixels. Right. These are all, this pixels depth value is 5. The next row 5, the next row, next row. Basically will come from top to bottom. So the top row scan line, 5, all the pixels depth value is 5. How we calculated this depth value, I'll talk about that in a bit. The second row, calculate all the depth 5. Let us say all the pixels depth value is 5. Now essentially what you need to do is you need to compare those 5 with this infinity values. Whichever is smaller, you replace that with this infinity. For example, come from the top row. The top row here, the top row, all the things are, all the pixels are infinity. Now here, in our case, the top row is 5. So compare this 5 with the original infinity. So 5 is less than infinity. What you do is replace this infinity with 5. So your depth buffer will now become 5, which was infinity here. This 5 is compared with infinity. 5 is less than infinity. So write 5 here. Next pixel, that is x plus 1. Next pixel was infinity. Now that infinity will be compared with 5. So 5 is less than infinity. So replace that infinity with 5. The next pixel, x plus 1, was infinity. I can say first row, that is the top row, third column. Top row, third column is infinity. Now top row, third column's depth is 5 value. So 5 is less than infinity. So in that case, replace that infinity with this value. So similarly, you do the x plus 1, that is the top row, 5. So how many 5s we have? 7 5s. How many infinities we have here? So 8 infinities. 7 5s we have. So 7 5s with 1 infinity. So the top row is open. So come with y minus 1. That is the next bottom row, bottom scan. So bottom scan line, we have 5 6 5s. So initially we have 8 infinities. Now we have, that means 8 infinity in the top minus 1 row. Top minus 1 row, we have 8 infinities. Here we have top minus 1 row, 6 5s. So every pixel, that is, let us take this 5 now. This 5 is compared with infinity. 5 is less than infinity. We'll replace our infinity with 5. So we get how many? 6 5s here, remaining 2 infinities as such. Now we'll focus on top minus second row. We have 8 infinities here initially, and top minus second we have 5 fives here. So replace those 5 fives here, and 3 infinities remains as such. Next, top minus fourth row, all infinities, that is 8 infinities. You write 8 infinities here, and then in your image, top minus fourth row, we have 4 fives. So write 4 fives, remaining 4 infinities. Like this, it goes on. 1 minus 1, 1 minus 2, 1 minus 3, 1 minus 4, 2, you can see. So all these 5, 5, 5, 5, 5, it comes here. So remaining is all infinite. Now, this is the story of depth buffer. Now comes the story of screen buffer. Now, whichever is infinity, don't fill. It is neglect. Now, whichever is 5, 5's depth. 5 is the depth, that is the top row's first pixel is 5. Now, what is 5? 5 means this purple color pixel. Show that purple color pixel in the screen buffer. Screen buffer is initially empty. That means all black pixels, you are not seeing anything. Now here in the top row first column, whatever is the depth buffer content, 5. 5 means this 5 means this purple color pixel. So plot it. Next is also 5, plot it. Next is 5, plot it. Like this 7 5s, 7 pixels you will plot. 8th is the infinity, don't plot it. Come to top minus 1 row. There are 6 5s, so 6 5s plotted. 2 infinities, don't plot it. Next row, there are 5 5s, 5 purple color pixels, 3 infinity, 3 infinity. So like this it goes on. Now, don't you think it's very simple? So you had to project this, you had to show this to the screen. So in the screen, we somehow show this. But visibility surface detection means what? If I have more than one image, and if they coincide, either full or partial or whatever, you need to show those pixels which are visible. So taking only one scene isn't enough to understand this result. So what we will do is, we will take another example, not another example, another image, something like this. Now this image is overlapped onto this purple image. Now, since this is these are all new pixels, it is our responsibility to calculate the depth of each and every pixel. We will somehow calculate, and let us say the depth buffer is filled with these values. Means what? This pixel, the topmost pixel's depth is 7. Let us say, example. Next, come down the next scan line. Let us say there are 2 pixels. 2 pixels depth is 6 and 7. Next, come down. Let us say there are 3 pixels. 3 pixels depth is 5, 6, 7. Like this, you go on. This is your depth buffer for this image. This is your depth buffer for this purple color image. This is your depth buffer for this orange color image. But the beauty is, this orange color triangle has been overlapped onto this purple color triangle. So it is we should carefully determine which pixel is visible, which pixel is hidden. If we overlap this orange triangle onto this purple triangle. Alright, now how do we calculate it? Now take the output of the first image. This is the output. This is the depth buffer. This is the screen buffer. Now depth buffer is this. Top row 5, 5, 5, 5, 7 5s infinity. Top minus 1 row 6 5s to infinity. This is the output of this purple color. Now we will take this output. Now we will match with this. Okay. How? Top row first column is first cell is 5, whereas here it is 7. Okay. Now here it is 5 and here it is 7. So 5 will be compared with 7. Which is less? 5 is less. So write 5 here. Next. Top row second cell, that is 5. 5 will be compared with this empty now. Empty in the sense you can consider as infinity. So this 5 will be now compared with infinity here. So 5 is less than infinity, right? 5 as such. Next. Top row third cell is 5 here. And top row third cell is empty here. It is infinity. So 5 is compared with infinity. It is less. So write 5 as such. So it goes up till 8 cells. This is infinity. Okay. Top row is done. Next, come to the second row. Second row, first cell is 5. Here, second row, first cell is 6. So 5 will be compared with 6. 5 is less than 6. So the least value is 5, right, as such. Next one. Second row, that is top minus 1 row. Second cell is 5. And here, top minus 1 row, second cell is 7. So 5 will be compared with 7. So the lesser value is 5. So write 5. Next. Top minus 1 row, third cell here is 5. Top minus 1 row, third cell here it is empty, infinity. So 5 will be compared with infinity. 5 is less than infinity, write 5 here. So it goes up. Next. Top minus second row, that is 5, will be compared with 5. Here, top minus 7. So 5 is less than 5 or equal to 5. So write 5 as such. Next. This 5, that is top minus second row, second column, 5 will be compared with top minus second row, second column, or 6. 5 is less than 6. So the lesser value 5. So it goes. Fourth row, it is all 5, 5, 5, 5, 5. I mean 4 5s, 4 infinity. Here, 5, 6, 7. No. 4, 5, 6, 7. 5, 5, 5, 5 here will be compared with 4, 5, 6, 7 here. Now comes the magic. So this 5 is compared with this 4. So which is lesser? 4 is lesser. So replace the old 5 with 4. Next also it is 5. Check that 5 with this 5. It is same. So either you can, you should replace with don't replace, just keep it as such. Next one is, this is 5. 5 will be compared with this 6. So 5 is less than 6, write 5 as such. Next comes the magic. Infinity, here it is infinity. And here we have 7. So infinity will be compared with 7. So 7 is less than infinity. Write 7 here. Next row, 5, 5, infinity, infinity, all these guys will be compared with 3, 4, 5, 6, 7. So 3 is less than 5. So write 3. 4 is less than this 5. So write 4. 5 is less than this 5. So write 5. 6 is less than this 5. No, 6 is not less than this 5. But here it is not 5, it is infinity. So 6 is less than infinity, write 6. 7 is less than infinity, write 7. Next, 2. Here we have only one value, 5. And rest all infinities. So 2 is less than infinity, write 2. 2 is less than what? 5, 5. 2 is less than 5, write 2. 3 is less than, now comes infinity. I'll repeat the last row, 2, 3, 4, 5, 6, 7. Here we have 5, infinity, infinity. Now compare 2 with 5. 2 is less, so write 2. Replace it. Next, 3 will be compared with infinity. So 3 is less than infinity, write 3. 4 will be compared with infinity, right? 4 is less than infinity, write 4. 5 is less than infinity, write 5. 6 is less than infinity, write 6. 7 is less than infinity, write 7. The remaining don't touch. Okay. These are all infinity. Okay, this is your depth buffer. Now what happens to screen buffer? Now, whichever is 5555, that is the old guys. Old guys means here. Just keep plotting your total guys. Now, wherever we have got the replacements, 4 here, 5 here, 5 here, 7 here, these guys, and all these guys, 3, 4, 5, 6, 7, 2, 3, 4. These are all the depth intensities of this orange color track. So wherever we got 4, 3, 4, 5, 6, 7, these days, you write orange. That is these pixels. What did we learn now? This orange replaced, it was what? See, it was purple pixel. Now purple pixel has been replaced with what? Orange. You see the last picture. This is purple, this is white, infinity. Purple, white, all this. Now replace with orange. Now you can take this guy. This guy was purple, now replaced with orange. So don't you think we are either hiding the not visible guy, or we are visible surface detection. We are detecting the visible surface. Both means it. Either you are hiding purple color, or you are showing orange color. So this is how depth buffer algorithm works. So basically, you need to have two buffers. Depth buffer should be filled with the highest value infinity initially. Screen buffer should be filled with darkness. I can say, or I can say not darkness, the background color, and then calculate the depth value of each and every pixel of all the images, and then compare with the depth, the initial depth buffer. If it is less, replace it. If it is not less, just retain the infinity, is the highest color. Next, once you are done with depth buffer, go to screen buffer. In screen buffer, whatever is the value of the depth buffer, you write the corresponding pixel. Keep on doing this for all the pixels. You're either doing this hidden surface removal, or that means you're not showing purple color, you're hiding it, or you're doing visible surface detection, or that means you're showing the orange. Either ways, you're doing hidden surface removal or visible surface detection. Now that we have understood via common sense, now we will see the exact mathematics. So yeah, you can see this. If I overlap in 3D or 2D, whatever, whichever pixels are visible will be shown. How? All this, whatever we discussed. Whichever pixels are, you can see here, yeah. This green portion, what is this, blue portion is overlapped with this green portion. So you are only seeing blue portion. Means in your screen buffer, you are only seeing the blue pixel. And here you can see green triangle has been overlapped on blue triangle. So in this portion, blue pixels are not visible. So only green pixels are visible. We understood, human beings. How do you make the machine understand? Follow these. So you fill with green pixels. Alright. That is why this depth buffer algorithm is very accurate. Okay, now we will apply all our common sense to our textbooks analogy. Alright. Now, this is very simple. Now let us say there are three images, S1, S2, S3. These are all basically planes. Now let us say here is where is your camera, X comma. Now if you look at this dotted lines means here is your view vector. That means from this in this way you are seeing it. Now what really the amazing feature is this red pixel is here, and in the same way this pixel is here, in the same way this pixel is here. So which pixels I should hide? This pixel should be hidden. That is this pixel of S3 because it is in the same line. You can imagine in front of you there are three pictures and you view it. So you will only see the pixel of the first image, and in the same direction the pixel of the second image will not be seen, and the corresponding pixel in the third image will not be seen. So that is what it is saying. So you will only see x comma y. That is S1's x comma y here. You will not see S2's x comma y and S3's x comma y. What are we doing? We are doing this hidden surface removal or visible surface detection. Yes. We have understood the algorithm. Now we'll put it into formal words. Alright. I told you there are two buffers, depth buffer and screen buffer. Depth buffer we initialize to infinity. I mean, here in his words, 1 means it is the highest truth. In the computer's words, 0 to 1. 0 is the least value. Next value can be what? 0 0.00000001, 0.00, whatever. This 2, 0, 2.3 up to 0.99999, and last value is 1. So in that sense, he has taken as 1. In our basic common sense, we can take it as infinity. Now, frame buffer, what did we do there? We took it as empty. So, or I told you black color. So here you're taken as, it should be actually background. So green triangle overlapped with blue triangle. So the background color is green. Fill all the pixels, background color as green. Right. So we have initialized. Basically, I am talking about this face. Which face? Yeah, this face. So initially, all the pixels of Z buffer is highest value, infinity in our case. In his case, it is 1. It is empty or background color in his case. All right. Step 2, yeah. For every projected pixel, that is for every pixel, calculate the depth Z. I told you that is these values. That is how exactly you got 55555. How exactly you got 767, 567, 4567, 23. These values you need to calculate. How? You will see. So somehow you calculate the depth Z We will see that somehow in 1 minute, I guess. Next, if that calculated Z means what? That 3, 4, 5, 6, 7 is less than depth buffers of x1, means that infinity. So if the calculated Z, let us say 3 is less than infinity, what do? You replace that 3 in that infinity position. So that buffer which was infinity, now it will now become 3. So means we are doing this phase. Which phase? Yeah. So it was infinity. Infinity will be compared with 5. So calculated buffer value is 5, Z buffer. 5 is less than infinity. So what do? You replace that 5 with infinity. Here. So all were, that is the top row first column was infinity. Here top row first column was 5. 5 will become, 5 is less than infinity. So yes, so replace that infinity with 5. So that is what this step says. Yeah. If Z, that is 5, is less than infinity, what do? Replace that 5 with infinity. Next step, what we did here in the screen buffer. In the screen buffer, everything was empty. Everything was empty. That means everything was background color. So since we now replaced infinity with 5, so whatever 5's pixel color, which was empty here, right? Yeah, it was empty here. Now will be replaced with purple. So that is what it says. Frame buffer, which was empty, which was background color, will now be replaced with that surface color. This the purple color. Purple color. So in the previous, that is the saffron, I mean this orange triangle, what happened? Come to this part, 4 part. So it was 5, that is the purple pixel. 5 is being compared with 4, that is the orange pixel. So 4 is less than 5, replace 4 here and replace the purple pixel with orange pixel. So that is what it says here. Replace that surface pixel, surface color, orange, with this frame buffer, purple. So what happens now? So that buffer is 4 now, that is the orange pixels depth, and frame buffer, that is which was purple color, now it becomes orange color. So after all surfaces are processed, depth buffer and frame buffer will store correct values. Means after all the pixels are processed of all the polygons, of all the faces, depth buffer and frame buffer will have correct values. Now coming to the main purpose, that is how do you calculate this Z? That is how do you calculate all these days 5, 5, 5, 5, 5, and these days 7, 6, 7, 5, 6, 7, 2, 3, 4. These, how do you calculate this Z? Because if you know how do you calculate, then only you can compare it. If the calculated Z is less than depth, that is if 3 is less than infinity. So how do you calculate that 3? The answer is here. Okay. We know the plane equation ax plus by plus cz plus d is equal to 0. This we know. At any surface position, since the depth means it is directly associated with the z value, the z coordinate. So take out z from this equation. So that means substitute, put all the other guys towards the right side. So it is minus ax, put plus by this side, it is minus by, d this side, it is minus d, and z's coefficient is c, so that will be pushed a bit now. So this is your z, means to say this z, how do you calculate? From the plane equation, put everything that side, this is your z. Now I told you in this, here. Once you fill your frame buffer, it was infinity here. The top row, first column, first cell was infinity. and we calculated phi. How? This equation, plain equation, ax plus by plus cz pz plus d is equal to 0. Z is equal to, you push all the other guys towards right side, denominator, all the stuff. So you'll get some value. Let us say 5. So 5 is now compared with infinity. 5 is less than infinity. You replace infinity with 5. So you replace infinity with 5. Next, what you did, you went to the next pixel, that is the top row, next pixel. So how do you put it in, how do you make the algorithm understand? That is, like, what is the algorithm? So the same row, next position, that is the X position is getting varied, not the Y. So if we imagine this as, if we imagine this as X, so this guy is X plus 1, this is X plus 2, X plus 3. So X increments. And once you are done with the first row, you will now come to the second row, that is Y minus 1. Y minus 1, Y minus 2, it goes. So for every Y minus 1s, you will go from X to X plus 1, X plus 2, all the stuff. So in my algorithm, I'll put it cleverly like this. Yeah, here. So for any scan line adjacent X position, that is X plus 1. So wherever you have X, you write X plus 1. And since this is the new depth value, see here, let us, take this second row, the top minus 1 row, top but 1 row. The first guy is 6, second guy is 7. So 6 is considered as Z and 7 is considered as Z dash. So yeah. So for the X plus 1 position, so replace X with X plus 1 and call the entire guy as Z dash. That is the next guy. Now if you, if you multiply minus AX minus into plus minus A minus BY minus D by C, and then you can easily substitute, because it is minus AX minus BY minus D by C, I can write it as Z. So entire thing can be written as Z minus A by C. So what you essentially do is give this A to these guys. It is minus AX minus A minus BY minus D by C. So minus AX minus BY minus D by C is your Z. So it is Z minus A by C. Now, since after, you're done with one row now. So next row is what? We should come down, right? So once, because it's recursive, once the you will come down a bit. So that means Y here. You were here, right? You were here 7, and you come down means it is Y minus 1. Again, come down means it is Y minus 2 minus 3. But X, the point is X should come down. We cannot say as X minus 1. So here it is say X plus 1, X plus 2, X plus 3. But the moment you come down, because it is in the diagonal, it is slope. So you have to calculate X slope. So X slope downwards, that is the new X is the old X minus 1 by M. This we have seen in our class, on campus class. There is DDA, we're doing DDA midpoint line. Whenever you want to go up, it is X plus 1 by M. Whenever you want to go down, it is X minus 1 by M, where M is the slope. Now what you do is, you write X wherever you have X minus 1 by M in this equation here. Minus A into, wherever you have X, you write X minus 1 by M minus BY minus D by C. That becomes your Z. For the next coordinate, that is this Z dash, wherever you have X, you write X minus 1 by M. That means, simply put, replace x minus 1 by m in both the equations, in z as well as z dash. So the new z dash, here we got as z minus a by c. Here we will get z dash as z minus a by m plus b by c. Just do it, it's a simple mathematics. So I'll repeat, the top row's first column is z, that is this. Top row's second cell, x plus 1 is this. And you do the mathematics, you will get the new z dash as this. You need not have to do this, you can simply take this itself, no problem. So only, if you solve this, you will get this. So these two equations, you should keep on doing. I mean, this equation especially, z plus z dash, keep on doing for the entire first row. Second row, that is the top minus 1 row. So y minus 1. And in fact, of course, you should do, wherever you have y, you should write what? The second row, y minus 1. Is replace y with y minus 1. And keep on doing this and replace x with x minus 1 by 1. You will get this. So yeah, this you can see the top scan line. You should keep on coming from top row, next one, next y minus 1, and x plus 1, x plus 1, x plus 1. So all the rows will be completed. If you keep on doing this, you will ultimate. I really like this line here. Yeah. After all surfaces are processed, depth buffer and frame buffer will store correct values. Means here, after all the pixels are processed, depth buffer and screen buffer, the frame buffer will have correct values. Means to say, mathematically, if you do all these 4 equations recursively, you will get those frame buffer and the screen buffer. I mean, the depth buffer and the frame buffer or the screen buffer with correct values. Hence, you will see these kinds of images. Whichever is visible, you will see. How? This is how it is. So orange is visible, orange you will see. Purple is not visible, you will not see purple. Whereas here, the first row case, purple is visible and orange is not overlapped here. So you will see purple. You will not see orange. Whereas here in the bottom row, you will see orange has been overlapped with purple. So purple you will not see, you will see only orange. That is what I mean by hidden surface removal or visible surface reduction. Okay. So all these are done. So summary is you need to make sure that whatever we see should be made understood to the system. We human beings, we understand, but somehow you need to make the machine understand which pixel is visible, which pixel is not visible. So that is what we did all this way. So there are 2 ways, backface. I mean, many algorithms, but there are 2 approaches: object space and image space. Object space backface detection, that is called culling, which is not that efficient. Next one is image space depth buffer algorithm, or the Z buffer algorithm. That is what we saw. And there are others: A buffer, scanline, ray tracing, using your binary search tree as well. Many things. So you don't have to study about this. The last part of this phase of this discussion: Opengl visibility detection functions. That means through open, see all these, we have understood the theory, mathematics, everything. But we need not have to do all these pixel by pixel. We have Opengl standard inbuilt functions for backface detection as well as depth. For backface, what we have, since it is backface removal, hidden surface removal, that is the object space method, I told you it is culling, that is eliminating the back pixels. How exactly we eliminated? You remember this? Yeah, this one. If the plane equation is less than 0, it is front face. If the plane equation is greater than 0, back face. So here also we have written hull face, back face. Back face has to be culled, has to be eliminated. So we have that algorithm, that inbuilt function. Yeah, yeah. First you need to enable it and cull face. So mode means which mode you need to remove, either move front one or back. In the third and fourth algorithm, we saw this. Right? If you traverse counterclockwise, it is visible. If you traverse clockwise, it is not visible. So if you do this, cull face, indirectly cull face is what gets applied. Orientation matters. That is where exactly your lookup, GLU lookup is visible. And for Z buffer, that is the image space. The depth buffer algorithm, what all OpenGL functions we have. We have enable. We have any display mode. You remember we had written this in glut init display mode of glut underscore depth. We had written glut underscore double or glut underscore depth. Those two will be odd. So, and then you need to enable the depth test. We had written this in our lighting program. Not the lighting. There we had enabled light. Here we had, the third program and the fourth program, we had written this GL enable, GL depth test. And you can clear the depth buffer bit. Depth functors is also used to analyze how exactly the Z buffer varies. So these are the various you can test the condition as well, even if the Z buffer is less than any other image Z values. So using this depth func. All right. So these are the various OpenGL visibility detection, along with others. But these are the main via OpenGL how exactly you can perform hidden surface removal or visibility surface detection, detect visible surface. So this completes this module 4's visibility surface detection methods. I sincerely thank your time. Thanks for watching this. And as usual, any doubts, please put it in the comment section and I will address all of them personally. And thank you.